Hello and welcome back to an electronic basic video. In this video I'll explain the basics of transformers. But before we start though, a little warning. In this video I will show circuits with lethal voltages, so don't try this at home, just watch the video. Also, this video is a little bit more advanced than my other videos, so if you know absolutely nothing about electricity, I will give you a very basic explanation of a transformer in the beginning of the video. Feel free to skip the rest of the video if I'm confusing you too much, and also turn on the subtitles if you don't understand me. Okay, let's begin. In layman's terms, a transformer is a device that converts a voltage to a higher voltage or a lower voltage. So let's say we have a voltage of 10 volts AC and we want 20 volts AC, we can use a transformer to step up 10 volts to 20 volts. The output voltage of that transformer is determined by the number of turns that a copper wire is wrapped around a core. The core of a transformer is made out of steel and looks a bit like this. So let's say the first coil has 10 turns and the second coil has 20 turns, and we apply an AC voltage to the first coil, we would get double the voltage on the secondary coil. If we however connect an AC voltage to the secondary coil, we would get half the voltage on the first coil. So here I have the transformer. As you can see here, there are 3 windings, just ignore the middle one for now. This is the primary winding, and as you can see it has a lot of windings, and then we also have the secondary winding which has a little windings. So, if we connect a voltage to the primary winding, we should get a lesser voltage on the secondary winding. This transformer is rated for mains voltage, so 240 volts. So if we connect 240 volts here, we should get a lesser voltage on here. And this is exactly what I did, but with another transformer. This transformer is unfortunately broken. So, I have modified this PCB and transformer to output a AC voltage. This AC voltage is measured on this multimeter. This is the secondary voltage, and the primary voltage goes from the mains. So this is just flipped on by the breaker, and then as you can see we have 11 volts at the secondary output, while we have at the input 200 volt RMS. And this is correct. So we connect it to the primary of the transformer. From the primary it goes to the secondary, it reduces the voltage, and then we read it on the multimeter. Now if I was to reverse the primary and the secondary voltage, so that's 240 volts on the secondary and the other voltage, the primary voltage on the primary, we should get 5200 volts. This is unfortunately not really possible with these transformers because the impedance of the secondary coil is too low at 240 volts, and thus will result in a high current and maybe even a short circuit, and this is not ideal. And without modification on the PCB this would also not be possible because the capacitor and diodes would also just blow up. Okay, now that the basics are out of the way, I will explain a transformer with math. A one-phase transformer exists of 3 things. A core that is most of the time made of iron and made in sheets to minimize eddy currents, a primary winding and a secondary winding. If we connect an AC supply to the primary winding, we will get a current that flows through that winding. We get a current because current is equal to the voltage divided by the impedance, and the impedance is the square root of the resistance of the copper wire plus the inductance squared. And that's why we get a current running through that wire. Okay, now that we have a current running through a coil, the law of Hopkinson states that the flux created by a coil is equal to the number of windings the coil has times the current divided by the magnetic resistance. And thus we get a flux induced in our inductor. An inductor is just another word for a coil, and a coil is just wire wrapped around. Okay, now the flux will travel through the iron core and thus also affect the secondary coil. Because of that we get an electromagnetic force or a voltage induced in a secondary winding. We can calculate the induced voltage with this formula. The created voltage is equal to negative times the turns times the flux times delta flux, divided by delta time. Okay, now we got the absolute basics out of the way. It's time to explain a single phase transformer with losses. I will explain this with a vector diagram to make things easier. When we connect an AC supply to the primary with no load connected to the secondary, we get a current that we will call I0. This current, as previously stated, is simply calculated by dividing the voltage by the impedance. This will induce a voltage in the secondary coil, again as said before. If I connect a load to the secondary coil, like a heater, a resistor, an LED, a motor, whatever, there will also run a current through the load and also through the coil. But because there is no current running through the coil, we created a secondary flux in the secondary coil. This flux will be 180 degrees phase shifted and thus will neutralize the original flux. If this happens, the voltage on the secondary coil will disappear because, as previously stated, E equals minus N times flux divided by delta T, and if we change the flux, then we change the voltage, and if we change flux to 0, then voltage equals 0. This would obviously result in a very bad working transformer, and in reality it doesn't really work that way. To compensate for the changing in flux, the primary coil has to increase the current and thus increase the flux. The increased flux we can call phi1, and phi1 primary objective is to neutralize phi2 so that way phi0 remains in the core and thus creates a constant voltage on the secondary coil. Phi0 always has to remain constant because if it doesn't, then the voltage changes on the secondary coil. Okay, that was a lot to take in, but to recap, if we connect an AC supply, we create a flux phi0. This flux has to remain constant in the core to keep the voltage on the secondary coil the same. If we connect a load to the secondary coil, the secondary current will also create a flux phi2, and that phi2 is in the opposite direction of phi0. This will decrease the flux in the core, and because the flux in the core has to be phi0 to have a constant voltage, the primary coil compensates for it by demanding extra current. This current increases the flux, and we call this increased flux phi1. Phi1 is equal to phi2, but it runs in the opposite direction, so they neutralize each other. And thus, if they neutralize each other, only phi0 is left in the core. And thus, we get a constant voltage on the secondary coil. If I'm still confusing you too much, I've set up this little example that will hopefully clarify some things. I've set up the transformer here that is connected to the main, so 220 volts, and the secondary coil is connected to these alligator clamps, and these I will connect to a load, and when we connect a load, the primary current that runs through these wires should increase, and we will measure that current on this multimeter. So we have about 60 milliamps in the primary coil, and when I connect the secondary coil to a load, we should see the current increasing. So I will connect it, and as you can clearly see, the current jumped. So what just happened? I connected a load so that a current runs through the secondary coil. Because the current runs through the secondary coil, phi2 is created and neutralizes phi0. That is not good, because the voltage would change on the secondary winding. So that's why the primary current increases and thus creates an extra flux, phi1. Phi1 neutralizes phi2, and thus phi0 remains in the core and creates a constant voltage for our secondary coil. And we could observe that extra current that is demanded for the increased flux through this meter. Let's now draw the diagram that I talked about earlier. But first I will introduce you to the fixed variable k. K is calculated by dividing the number of turns of the primary coil by the number of turns of the secondary coil. So let's say the primary coil has 10 turns and the secondary coil has 20 turns, and K would be equal to 0.5. We could also calculate K by dividing the secondary current by the primary current, but that's not that easy. Also, K is a constant and is decided by the manufacturer. You cannot change the K factor without modifying the transformer. Okay, now I will begin drawing the vector diagram. We will begin by first drawing our secondary voltage. This is the voltage we would measure with a multimeter on the output of the transformer, so the secondary coil. Then I will draw the secondary current under an inductive load, so the current is lagging the voltage a bit. Next we will draw the primary current. The primary current exists of two components, namely the excitation current I0 and the compensating load current I accent 1. The excitation current also exists of two components, namely the current caused by iron losses Ig, in other words the working current, and the current Im that caused the flux Phi0. We can also call it the magnetizing current. If we create a coordinate system with Phi0 on the y-axis, Ig, the working current, would be on the x-axis, and Im, the magnetizing current, would be on the y-axis. The complex sum of these two currents would result in the zero load current. If we add this drawing to our vector diagram, it would look like this. Now, if we want the total primary current, we also need to add the zero load current together with the compensation load current to get the total primary current. Also note, the compensating load current is 180 degrees phase shifted relative to the secondary current. Because coils have an ohmic resistance, we need to calculate the voltage drop. We can calculate the voltage drop by multiplying the resistance of the wire times the current. We need to do this for both coils, and the voltage drop is in phase with the current that runs through the coil. So we need to draw the vector here and over here. The primary coil and the secondary coil create magnetic fields, but these magnetic fields don't always go through the core and to the other coil. So some of these magnetic fields actually get lost, and those cause an inductive voltage drop. We can calculate that voltage drop with this formula, I times XL accent. Again, we need to calculate this for the two coils, and the inductive voltage drop is leading 90 degrees on the current. So we need to draw the vectors here and over here. With these vectors we can calculate the input voltage of the primary coil and the output voltage of the secondary coil. Keep in mind that the secondary output voltage E2 is without losses, and U2 is the actual output voltage we would measure with a multimeter. Okay, so we can mathematically calculate E2 and U1 with these formulas, and when we draw it on our vector diagram, it looks like this. Now you can see that U1 is the actual output voltage we put on our transformer, but E1 is the actual voltage that's on our transformer that's actually doing the work, and E1 is with the losses, and U2 is without the losses. And of course the same can be said for the secondary coil. So U2 is the voltage we would measure with a multimeter, and E2 is the voltage that comes out of the coil but without losses. And when we subtract the losses from the ohmic resistance and the inductive voltage drop, we get U2. Okay, this is the basics of transformers. I will leave it here for this video. There is a lot more to cover, like different frequencies, calculations, power factors, different loads, three-phase transformers, and a lot of other things. But maybe that's for another video if people are interested in a deep dive.